Okay. Our first speaker today is Laurent Arditi of ARM in Sofia. His topic is an efficient methodology to find bugs using ABV, Assertion Based Verification. Laurent has worked for ARM for 8 years, first as a modelling engineer and now as a formal verification expert. He leads the formal verification activities within ARM as well as applying formal verification to microprocessor development. So we're going to hand over to Laurent. Hi, Laurent.
Thank you, Mike. So good morning or good afternoon, depending on where you are. So I will present some aspects of ABV that we have been using within ARM for quite a few years now and providing good results. So first, what do we need to look at when assessing a methodology or a technique in general? I would say that all managers are interested only in quality and schedules. That means actually on return on investment. So the question is, what kind of ROI can we get from ABV? So first, what is ABV? This is assertion-based verification. That means that verification team or design team have to write a set of assertions that will be verified against an RTL design. Usually these assertions are low level. That means that they directly speak about the design itself. They are not something really high level saying, oh, that CPU will correctly, for example, it will correctly execute all programs. There are a lot of different classes of assertions. So I say usually they are low level about the designs, but we can think about other classes of assertions like the ones checking for X-propagation. We have also a lot of assertions to verify standard protocols. And we have some more higher level assertions. Usually, we want these assertions to be used in all our verification approaches. That means simulations, formal verification, emulation, and why not FPGA also, or even test chip. We are not doing that right now, but maybe in the future. So in the rest of my presentation, I will show how we can achieve a high ROI using ABV. And I will illustrate that with some examples coming from real developments of ARM CPUs or design more generally. I'm a formal guy, so I will put a bit more emphasis on formal verification, but not only. So this is a nice, or not so nice picture showing ABV. It's actually a bit difficult to illustrate in a picture what is ABV. So I try to do that here. It's not perfect. So in the ideal case, we start from specifications. From these, designers write an RTL, and other people or the same people write assertions. Then we combine these two, RTL and assertions, for ABV. That means we run these assertions into simulation, formal, or emulation tools. From that, we can get bugs. This is what we are looking for. And we can get some metrics also, like what do our assertion cover into the design. There are new kind of tools also which are able to automatically generate assertions, and these assertions are also used for ABV. And this tool can get some feedback from the coverage and other metrics. I will show that that can significantly increase the ROI of ABV because that comes almost for free. We don't need any people to write this new assertion. So first, embedded properties, we call them also designer properties. We run them in formal, but we also run them in simulation and emulation, as I said just before. sometimes we want to rewrite some assertions so that they are more efficient in simulation or in formal, for example. So we have a collection of tweaks for that. I will not get into very deep details, but I can mention that, for example, we use oracles and pseudo-constants to model non-determinism. This is something that we can do for formal, but not for simulation, unfortunately. So a very simple example is if we want to ensure that in an array we don't have two cells with the same value. For simulation, we need to do two nested loops that will generate a lot of assertions. For formal, if we use pseudo-constants, we just need one assertion that is checking two indexes which are non-deterministically chosen. We use a lot of structural symmetry also, that is mostly to reduce the number of assertions. So in a big design, we can have 10,000 assertions, and we are limited into the time and computing power that we can use to verify all these assertions. So we have to make a choice, and usually your good choice is to say, oh, I have that symmetry into the design, I will only verify a part of it, but we can put more effort on that part instead of putting a low effort everywhere. What is really making ABV efficient, I would say, is having interfaces between the main blocks which are defined formally or which are specified using assertions. So if we have a very big design, we identify the main blocks at the first level, and we want the designers to write complete interface specifications. Complete means that when we use these assertions as constraints, we are able to black box some big modules. And this is very useful because, especially for formal, the size of the design really makes a huge difference. And these assertions are also verified in simulation at top level or at the block level. At the block level, the advantage is that they help defining the test bench. You can ensure that the test bench are not generated illegal values. Okay. So we have some rules which are mostly used for formal verification, and we ask the designers, for example, to write assertions using implications. So usually an assertion can be written in English language with something such as, if A happens, then B must happen. And that is really an implication. A implies B. So we ask the people writing assertions to use implication as much as they can. And the advantage is that it's more readable, it's simpler, but also it gives the first coverage information. Because if we want to verify A implies B, and we are not able to cover A, that means that we are not verifying anything with this assertion. So we have the first metrics for free if we just write assertions using implication. Well, as I said before, we disable assertions which are in very similar instances just to reduce their number and put a higher effort on the remaining ones. Also, we want to be able to use results coming from formal in order to decrease the simulation effort. So here the idea is to look at all the proven assertions and simply do not run them in simulation for speed concerns. Now, I'm going into more specific kind of assertions. The first one are checking for X-propagation. So everybody knows here that in simulation we have a lot of troubles with X's because of X pessimism and X optimism, and usually they are combined, and two different simulators will not do the same, and so on. So usually we can say that we cannot trust our simulators when we are in presence of X's. And this is especially true when we want to compare an RTL and the gate design, because at gate level we really X's are propagating, whereas in an RTL level the simulator will block the X's at some point. Also in simulation, usually we have a preamble into the test which will initialize some registers, and in reality it's not always true. So that again can mask some X's. So we have put in place a methodology based on formal verification that verify X-propagation with formal verification. We can do right by writing, we can do right writing some handwritten properties exactly as the embedded properties. So designers do that when they identify a signal which must never be at X. It can just write properties that will check that. But we also rely on the standard protocol checkers. For example, for ARM we use mostly AMBA, X3 or 4. And into these protocol checkers we have assertions that we test for X's on some dangerous places. But probably the most interesting properties for X-propagations are the auto-generated ones. For that we rely on the tools. And there are different approaches that you can use, for example, checking that all resetable flops are never at X. This is something that we do, but we have more complicated cases also that we want the tool to automatically generate. And for that, into a typical CPU, we get several thousand of properties, and that will be impossible to write them manually. Debugging of X-propagation is very easy when the failure comes from formal, because the test case, the waveform is very short. And also into the waveform we can clearly see the X is propagating from signal to signal. I have to say that very often we have failures with X propagations, but it's not very clear whether it is a functional issue or not. But in most cases, the designer fixed the issue because we don't know, maybe that one, the one that we are seeing is not important, but if we fix it, maybe the same property will fail again, and that will be a real bug. So at the end, we want to be completely clean on X-propagation and have zero failure. Now, we have found that ABV is also very good to verify more exotic features, I would say, mostly related to clocking. So that includes clock gating and clock enables mostly. In our design, we have more and more complicated clocking schemes, saying that one block has a running clock while the other has this clock which is not running, and we have some protocols in order to put one block into sleep and to wake it and so on. So here again, we rely on auto-generated assertions. So here on the slide, I will not detail you, we have some examples. We have found that we run these assertions into simulation and formal, and we have found that formal is very good to find the bugs, because usually the bugs are really tricky corner cases. An example is that one block is sleeping and he receives a signal to wake up and at the next cycle, combination of events. And actually, the block is not completely awake when it receives the events, and we have the bug. In simulation, it's very difficult to reproduce that because it is very timing sensitive. And also in simulation, we cannot afford to put blocks into sleep and non-sleep mode too often, because otherwise the simulation will do only that and nothing else. Now talking about high-level properties, this is probably the most difficult application of ABV because it needs a lot of human effort. Obviously, high-level properties cannot be automatically generated. Usually, they rely on some verification-specific components. Like, for example, we want to verify that in a cache, we don't have 2 lines for the same address. So for that, we need to spy the content of the cache. And we can do that only if the cache one itself is designed for that. We have applied high-level, I would say high-level ABV for very important concerns, like I say cache line duplication, but also coherency in multi-core CPUs. And also we wanted to verify that an implementation of a memory system complies with the hard architecture. Here the properties are more complicated, and the big difficulty with them is that in their cone of influence, they have almost the full design. So the complexity of getting proofs for this is very, very high. So for that, we don't want to get full proofs, even if we are using formal verification. Usually the target for formal verification is to get proofs. When the properties are too difficult, we are not expecting that, and we are not investing too much effort into that, because we know that it can take a very long time. But still, using the bug hunting approach, that means that we have only wooden proofs, we were able to find a lot of bugs. So that means that ABV, if we stay pragmatic, ABV is very interesting for us. Okay, so some other tweaks to help ABV. This applies for simulation, but also for formal. One very important one is to use design mutations. That means that we want to reduce basically the size of the design without removing functionalities, but just reducing the size. For example, if we have a big FIFO, we just reduce its size, so we have more chances that we get the FIFO full, and we all know that the bugs happen when the FIFO is full, not when it's half filled. So this is very good for simulation because we increase the probability to get into bad corner cases. And for formal too, but for formal, we must take care that we run formal with and without the mutation, because having the mutation can also hide some other problems. We try to use dynamic configurations. That means that instead of having multiple static configurations of the same design, we replace some parameters with what we call air wires, which are undriven signals. So one example is if we have a cache with 3 different sizes, in the real design that we release to the customer, this size is statically configured. But we can also configure it using an undriven signal. So the advantage in formal is that the formal engine will figure out which value of the configuration parameter must be set so that we can show a bug, if there is a bug. In simulation, this is very useful too, because we need to compile only once, and then with the same image, we can run the different configurations. Now, usually ABV is applied, I would say, too late into the design phase. But we did some experiences to use it much earlier, and we have found that it's very beneficial. So the advantage here is that we can ask the designer to write assertions as they are writing the RTL design, and they verify them immediately. So the advantage is that if, for example, the simulation test bench is not ready, or the test bench does not implement a new feature, then the designer can just add the new assertion and check it immediately instead of diving into writing the big checker for the test bench. We applied that on a graphical project where the project was composed of different modules, and on a few of them, formal ABV was used very, very early. And well, the code from the design manager was that formal bring-up was worked here for and also status overall time. This can be shown here. So on the left-hand side, you can see the bug distributions over time for all the blocks. So it looks like a Gaussian, basically, with most of the bugs being in the middle of the project. This is not surprising. On the right-hand side, we can see one module where we use formal ABV very early. So most of the bugs here are found in the first part of the project. I'm not saying that there were less bugs, but almost the same number of bugs, but they were found much earlier. And that means that the number of code churn, that means rewriting of the code, was very reduced for that module. So if we compare applying ABV early or late, we can see that early is much better because we can find the bugs at the unit level instead of at the system level, and that makes debugging much easier, and usually we don't have long loops to identify where the bug is, to assign it, to investigate, to fix it, and then reloop. So this is more localized, I would say. So now we are working on assessing ABV coverage because we always want to check where we are, basically, and with ABV, usually that's difficult. We write assertions, we verify them, and that's it. We don't know whether we are done or not. So what we want is to assess whether ABV is enough or not. There are some existing techniques based on code mutation. That is basically we inject faults into the design and we check whether they are detected or not. If they are not, that means we are not done. We need to write more assertions, for example. That applies mostly for simulation, not very well for formal. For formal ABV, we are looking at coverage in terms of what do the assertion cover statically in the design, so what is in their cone of influence. Also, what is covered when we prove an assertion, because sometimes we think that an assertion is very good, but actually the proof itself is very simple, and we don't need the full design. So we can measure that. And also, we can measure if we have only partial proof, what do we really cover. So from these results, we want to get which parts of the design are not being sufficiently covered by existing assertions. So here the answer will be write new assertions. And also which assertions are not pushed enough. And here the answer is either run for a longer time or try to optimize them or find some abstraction techniques and so on. So at the end, what do we want to show to our managers? The naive answer is usually, oh, I'm doing ABV, and at the end, I will show to the manager that the design is fully proven, the design is correct. But that can take a lot of months. So this is not what we want. What we want is to be able to show a lot of metrics during all the projects. So these metrics can be the number of bugs found by each methodology, of course, at what time, also the number of properties that are covered, that are proven, that failed and are not failing anymore, and so on. And managers really are keen to see an evolution. They don't want to wait 2 years and then you say it's proven, because usually you cannot, you never say that. You are not able to say that. My advice is to collect data from ABV on a very regular basis, and so collect the benefits, that is the number of bugs that are found, not really the number of properties that are proven, because managers don't care about that, and also show the cost. How many people work on ABV? That means how many people write assertion, how many people run the flow simulation, formal emulation, and so on. Also, what is the footprint on your cluster? I have other numbers here. So my conclusion is that ABV is a very powerful verification methodology. The good thing is that when we talk about ABV, that's usually for simulation and for formal. Emulation is coming also. It can deliver a high ROI if we use it carefully. That means that we try to automatically generate assertions. We don't spend too much time trying to prove them, but rather we focus on finding bugs. But ABV is not the magic bullet. We cannot verify everything with it. We still rely on simulation test benches because, for example, to verify data integrity, a checker in simulation is simple to write, but checking that with ABV is much more difficult. And we need to have some measure to assess the coverage and the completeness of ABV. Thank you. Any question?
Yeah. Thank you, Laurent. Thank you for the talk. We have quite a lot of questions online, but there may be some from Bristol first. Any questions from Bristol? Okay, we'll go to the online questions. First question from David Head. You are using a lot of formal. Oh, sorry. Yeah, you're using a lot of formal. What mix of engineer capabilities do you have? Do you have engineers dedicated to formal, or do all engineers use this methodology?
Yeah, good question. So we have a few number of engineers that are dedicated to formal. That means they develop the flows and the techniques, but they don't write the assertions, or very few assertions. We rely on the design team to write the assertions. So for a typical project, we may have 1 or 2 formal engineers, but that's it.
Okay, thank you. There's a question from Baz Art. Do you use an in-house tooling for generating X-propagation assertions? So it's a marketing opportunity for one of the EDA vendors, I think. So which tooling do you use for X-propagation? No?
So we use features that are built into the tools that we use, but we have developed also some scripts that run into these tools because we wanted more checks.
Okay, so you're saying you do use an EDA tool, but you put some script around it to make it more efficient.
Yeah.
Okay, thank you. There's another question from. Okay, no, sorry. One question for me actually. So that's the questions from online. We'll go to see if there's any questions. Any questions from Grenoble? Matthew?
No, no question in Grenoble.
Okay, thank you, Matthew. Ashish, is there any questions from Imagination?
No, we don't have any for this one. Thanks.
Okay, thank you, Ashish. Just one question from me, please, Laurent.
Yes.
One question from me. Just on the, you talked about doing some static analysis for coverage. What type of coverage metrics do you use for your formal verification assertions?
So it's a bit difficult to define a coverage matrix which relates to another matrix in simulation, for example. What we have chosen is something very similar to code coverage. So we use branch and statements coverage. And what we look at is for each branch or statement, if we change, for example, the condition of a branch, is there any assertion that will detect that we have changed that?
Okay, so that's a sort of mutation coverage, is it?
Yes, but this is a tool feature. We don't do the mutation explicitly.
Okay. Okay, thank you. There's one more question from online, from Vinay Kumar. Assertions mentioned used across simulation, formal, and emulation. How did you take care of emulation RTL hierarchy versus plain RTL simulation? So I think it's talking about how do you write your assertions for emulation as well as simulation. There may be a talk on that later.
So we write our assertions in system Verilog. So they are SVAs. And now, today, all the EDA vendors selling emulation can support SVA. Okay. Okay, so the EDA vendors support them for emulation, and we do have a talk on that later from AJ of Synopsys. Okay? Okay. No more questions, I think so. Thank you very much for your talk. Thank you, Laurent. Thank you.
Thank you.